In this section, we're going to look at some graphs and equations that involve some fractions, decimals, and negative numbers, things like that. For this one, let's stick with the fractions. So 2006, you bought the mower for $400. 2012, it was worth $320. Assume the depreciation or the loss of value is linear, so a steady decline. How much money are you losing? So it looks like in this case, the value of the mower went down by $80 over a period of 6 years. So you see, this one doesn't divide evenly. 6 doesn't go evenly into 80, but I can reduce a little bit. I think it would be 40 over 3, except actually that would be a negative because it's decreasing. So negative 40 over 3. So let's plot some points on the graph to see. So this is losing $40 every 3 years. Okay, so to graph this in part B, we've got the points 2006. Well, let's call 2006 year 0, because that's like when it was kind of a brand new mower. So 2012 would be year 6. So if we plot those points, 0, 400, and then 6 years later has a value of 320. So 6 is a little more than the 5. There's the 3. Looks like it'd be just under that line because that each one of those little lines is 25. So just under that. And let's try, I wonder if I've got a tool here to make a straight line. I probably do. Well, I'll look for that for another video. For now, I'm just going to draw it the best I can by hand. Okay, so it's looking something like that. That is not a perfect line, but pretty good. Okay, so using the graph, let's approximate the value of the mower this year. So currently, if it's this year, which would be now 2025, I wonder if that even fits on the graph anymore. 2025 would be year 19, right? Because 2025, 20 years later from 2006 would be 2026. So year 19, we're looking at something about like that year. And then we trace that over. Value looks like it's about, let's say $115 in 2025. Using the graph, approximate when it will be worth $50. So here I'm finding $50. Trace that over. And somewhere around in there, maybe about 24 years later, after 2006, so about 2030, around there. And now that may not be exact because my graph isn't perfect, but that seems like a good approximation based on the graph. Now let's get into the equation. So the equation would be the value V would be equal to 400 minus 40 thirds T, because it starts out at 400 and then it's losing $40 every 3 years. So that gives you your rate. So using this equation, let's find the exact value this year. So let's see. This year, remember 2025 would be 19 would be your t. So 400 minus 40 thirds times 19. I am going to go ahead and use a decimal for this one because we're talking about money in terms of the value, so that will be fine. So 400 minus 40 over 3 times 19, and we're getting 146.67. Okay, so that's telling me that my approximation from the graph was probably a little off, and I actually do see that line. I'm going to readjust my line now, see if we can better approximate. I think I dipped a little bit. That might be better. So I'm going to re-estimate at year 19. Oh, now that's looking a lot better. Probably about 160 on that estimate. So now I'm a little bit over, but now that's pretty consistent with that there. When you use precise graphing technology rather than trying to draw a line by hand, obviously it's going to be better. So now the question, using this equation, let's find when it is exactly $50. So we had an estimate, I think it's going to be more like over here now, so more than 25 years later. So in this case, when is it $50? So that means the value is $50 this time. So rather than plugging in the 50 for the t, we're actually plugging it in for the v. So this equation would be 50 equals 400 minus 40 thirds t, and then solve for t. So take away 400. That would be negative 350 equals negative 40 thirds t. So we can multiply both sides by the reciprocal. Negative 3 over 40. And again here, I'm going to go ahead and use a calculator and get an answer. So the negatives cancel out. So 3 times 350 divided by 40. And we're getting t, because everything cancels out there, equals 26.25. So that estimate's not too far off from what we had before. We said 24 years. It's actually more like 26 years. So the true graph would probably be somewhere between that red and blue line, according to the equation. Doesn't quite match up to our hand-drawn graph. All right, next slide. So a couple things here, just a couple interpretations. If the current net worth is $300, that's this point here, and it's going up $50 per month, okay? However, our point A is going backwards, so that's a negative 200. So what does that mean? Oh, negative 2 in terms of months? What does negative 2 months mean? Oh, well, that would mean 2 months ago. So 2 months ago, what was his name? John's net worth was, because it's in the past, $200. Now, point B, that's extra funky because we've got two negative values. That's negative 8, negative 100. So negative time means in the past. Negative money actually means debt. So here we would say 8 months ago, he was $100 in debt. Luckily, now he's saving, and so you can see this graph, as time goes forward, is going upward. So he's getting out of debt, and then, in fact, increasing his net worth. So good for John. Last page, just a little concept check. In general, how many solutions does a two-variable equation have? Okay, so for instance, if I just take a real basic one, like x plus y equals 5, there are many solutions to this, right? Because you could say, oh, 3 plus 2 equals 5, so that means 3, 2 is a solution. Well, 1.5 plus 3.5 equals 5. So that's another one, even like a decimal solution. Okay, you could have negatives. Negative 6 plus, what would that take? 11 equals 5. So that gives us another ordered pair. Negative 6, 11. So in this case, we actually have infinitely many solutions. So a one variable equation, if I just kind of write out to the side, if I just had like x plus 2 equals 5, well, in that case, there's only one variable, and the only solution that makes that true would be x equals 3, because the other number's locked in place. Whereas if you have two variables, you have a lot more wiggle room, so you actually have infinitely many solutions. And what does the graph represent? Well, those would be all the ordered pairs. That's why we would make our chart, we plot our points, your x and your y, and then you plot those ordered pairs onto the graph. So the graph represents all points that make the equation true. So that's why there's infinitely many points. There's infinitely many points on a line. Can data points be negative in certain situations? Yes, we actually just saw a couple of those. Some examples: negative money, we just said, would be like debt. Negative time would be in the past. And there are other, negative values that could come up in equations as well, just depending on the context.